That's the experience. Okay, thank you again. It's a great honor to join Joseph Saad and other speakers in this lecture series. I'm going to talk about preconditioning to accelerate neural network training, that is optimization. So we'll talk about how to construct preconditioners given the application in neural network. So this is a joint work with two of my students, Susanna Lang and Kyle Helfrich. So here's a brief outline. So since I'll be interested in deep learning, so I first will give you a very brief introduction of deep learning. So I'm lucky because Jay gave his talk first, so you already have the introduction there. So I'm going to be very fast going through the deep learning. And then we'll talk about very popular techniques in neural network training called batch normalization, and which is something related to what we're going to do. And then we'll turn to preconditioning. And then here's preconditioning for gradient descent. And then I'll talk about constructing a new preconditioning methods. When we talk about preconditioning, I will talk about a new theory, convergence theory, condition number-based convergence theory for neural network. And then finally, I will show you some experiments. Okay. All right. So first, I'm going to quickly go through deep neural network just to set up the notation. So first, here's the setting. We're going to look at supervised learning. So we have a labeled data set, which is a paired data, xi, yi. I goes from 1 to n. And the yi is the label for xi. So what we want to do is to find a model of parametric family of function, f of x theta. So y is equal to f of x theta to fit that data. That's all. So to do that, we need three things. Basically, first we need a model. So linear regression will be a linear models. Here we're going to look at the model based on neural network, and I will show you the neural network in the next slides. Once you have the models picked, say neural network with certain structures, then we need to choose a loss function to fit the model to the data. So we're going to define the loss between a model prediction, f of xi theta will be the model predictions, and yi is our label. So we want our model prediction f of xi theta to be close to yi. So we define the loss and try to minimize that loss. And the last step is to find the theta. Theta is the machine parameters, so the model parameters. So we try to find the theta to minimize the mean loss, the mean loss over the data set. All right, so first let's look at each of that in a little bit more details. So first, let's look at a basic neural network. So a basic neural network is simply a composition of L simple functions. So let's say example 3 here have composition of 3 functions. Each of that is a simple linear function. So let's say layer L is just the WL HL minus 1 plus BL. WL is a matrix, BL is a vector. So that's a simple linear function. And then composed with a nonlinear function G. This G apply on the vector element wise. Okay. So that gives us a nonlinear function f of L. So that defines HL in terms of HL minus 1. And then you have 3, in general, L of them composed together. So that gives you a very complicated nonlinear function. So basically build up a complicated nonlinear function from a very simple nonlinear functions. The nonlinear function GT, they are called activation function. Traditionally, things like logistic sigma is used, but nowadays it's more like ReLU function, which is just the maximum of t and 0. And you also saw that in several previous talks. So that's the model we're going to use. And then we want to define a loss. The loss depends on the task that you have. So if you have a regression task, their regression, you have the output y is a real vector, a real number real. Then the typically loss is a 2 norm of the error vector, so or mean square error if you take the mean loss. If the task is a classification problems like what Jay talked about in his talk, then typically it's the output y hat would be a probability distribution over the classes, and then the way to measure the loss that typically is called is this one called cross entropy. Okay. So once you have the loss defined, then all that's left is to optimize your model. So neural networks typically contains huge number of parameters. If you have many layers, each layer has a matrix, then the number of parameters is typically very large. So basically, gradient descent is the only options of first order methods. So a gradient descent like that, so lambda there, the step size typically is called learning rate. Now, a little bit more peculiar in the neural network optimization is that usually we use mini batch training or mini batch optimization, because deep learning, I mean, neural networks is a very, very powerful function. So you easily get overfit if you have a small data. So typically deep learning is used when you have a very large data set. So if you have a very large data set, you wouldn't want to train over the entire data set. So typically you take a big data set, you partition it into small subsets, mini batches, that's called mini batch. And then you train over each mini batch. So actually the training is done by sampling a small mini batch and then compute the gradient, approximate gradient over the mini batch, okay? And that's called mini batch training. Of course, the sampling involved is stochastic, so it's called SGD very often. But this is the first order method, so convergence you can expect to be very slow because in general the Hessian is very ill conditioned. So there are a variety of methods that have been developed in deep learning communities to accelerate the convergence. Yeah, go ahead.
Do I understand that each step you're using a different batch?
Yes, yes, each step you're using. So typically it's called an epoch. You have an entire data set, you partition into, let's say, K mini batch. So you train each step over one mini batch. Once you finish over the entire data set, it's called one epoch, and then you start over again with new partitions. Okay. So momentum methods is something like a conjugate gradient accelerations. So with the fixed beta, okay. Eta grad and RMS prop is actually in deep learning is regarded as called adaptive learning rate. It's as if a different learning rate for different coordinates, but it can also be considered a diagonal preconditioning. But although it can be considered diagonal preconditioning, but there's not really, it's not well understood in how it actually preconditioned, how the diagonal matrix improve conditioning number of anything. And Adam is something combined RMS prop with momentum basically. And also batch normalization is a method that's very, very effective. So actually, since we're going to look at close to batch normalization, so I'm going to just tell you a little bit more about the batch normalizations. So if I look at the one layer of the neural network, so it's just one layer, just the simple function. So the layer have HL minus 1 as input and then produce HL as output. And initially, of course, the H0 is just the network input. And then when I have a mini batch of n input, then when I do a mini batch training, then at the layer L, the input to my layer for the mini batch will be, say, H1, H2, Hn. I'm writing mini batch as X1 to Xn. Okay, so in this paper about that developed this batch normalization called BN, Alfie and Seghetti, they observed this. Okay, something called internal covariance shift. What they claim is that during the mini batch training, because of the change of input, then the statistics of this input A here changes. When you have a different mini batch input, then the input to the layer L, that statistic changes. In what I mean is mean and variance changes. And they think if that statistic changes, then WL, the way you try to train, will have to adapt to that change of statistics, because WL applied to HL minus 1. Now you have a different mini batch. What you're seeing is a different activation. So they think WL will have to adapt to that change. And they think that slows down the training. Another reason that you could have this internal covariance shift is if you have a neural network training. When you do the training, that your weight and bias changes over a very deep network. A small change in the weight and bias will create a large change in the later activations. So so that's they believe that that's the main reason that slow down the neural network training. So the remedy is simple. Just normalize the hidden variable statistics. So what I do is, let me just introduce a called a batch normalization operator. You take the AL, you subtract it by its mean here, subtract by its mean and divide it by its variance. Here, mu A is the mean, it's a vector, and then the sigma A is the variance, sigma A squared is the variance of A is that correction of the activations. So division here is element-wise division. Okay, so actually that's the notation I use throughout. It's actually used quite common in machine learning community. All the algebraic operation is just element-wise. And then they rescale that by a fixed gamma, and then add gamma is also a vector. So again, multiplication is also element-wise, and then add the beta. Beta is a shift, so recenter the data. Okay. So this is called, let's call it batch norm operator. So in the layer L, so HL minus 1 is the one that come out from the previous layers. So before you feed it into layer L, you apply this batch normalization operator on that, and then feed it to WL. Okay. So in this way, this HL, the normalized HL activation HL minus 1 will have fixed statistics, like fixed mean and variance. So,
so gamma and beta, what will they depend on H0?
Okay, gamma and beta for them is a trainable parameters. So they actually train. Okay, so it's actually just like W and B. So there's some extra trainable parameters. So it's actually going to be, they're going to train them. It's kind of like I fixed that mean and variance, but I don't know exactly what that should be. So you train them, okay, make them trainable. Yeah. Yeah, for each batch. So when you do the training, you feed in a mini batch. So you do that together, and at the layer L, you look at the mini batch input into the layer, and then get those mu and sigma. Yeah. All right. So so it's a fairly simple process, but it works wonderfully. So if you just use it, you find it accelerated convergence, and also allow the neural network to train with larger learning rate. And it also has also generalized better to testing data. Unfortunately, it's not very well understood. There are some limited analysis, typically just involving certain aspect of that and or a shallow network, like 1 or 2 layers network. I don't want to get into more discussions of that. But I want to mention some theoretical difficulties with this. So one thing is that this makes the network the batch norm operator there is defined from a mini batch. You have to have a mini batch feed into the network to be able to define that the batch norm operator. If you have only single input to the network, there's no minimum variance to talk about. So it's necessary to have a mini batch input. So that's done during training. But then in inference time, testing, of course, you don't have a mini batch. You just have one input samples. In that case, you don't have mu and sigma A. So what they do is just use the mu A and sigma A that they are computed during the training. Okay, some sort of means of the last training epochs. Okay, so another thing is that batch normalization doesn't work well when you have small mini batch size. So if the mini batch size is a hyperparameters. So if the mini batch size is small, as you can imagine, it's very volatile. So also, as I mentioned, it's not well understood theoretically. Then some problem is that when you generalize that to other network, like Qiang Ye, it actually has to be done, the batch normalization has to be done slightly differently. Okay, I'll mention that a little bit later. So there are several works that actually try to address these theoretical difficulties and things like batch renormalization, layer norm, group norm, and also group norm plus batch norm. All right, I think I will just mention those. Okay, so so that's some backgrounds. So let's switch to optimization now. So let's look at the preconditioned gradient descent. So let me first start the basic with gradient descent. So you have theta k plus 1, theta k minus alpha gradient at theta k. So if theta star is a local minimizers and the Hessian at the local minimizer is positive definite with lambda mean and lambda max being the minimum and the maximum eigenvalues, then you can prove this bound. I think this is in Josef's slides yesterday. Josef talked about that. And indicates in his book, the area up to consecutive area is bounded by R plus some epsilon for arbitrary small epsilon. And R is this maximum 1 minus alpha lambda mean and 1 minus alpha lambda max. So in order for this to converge, you need alpha, the learning rate, to be less than 2 over lambda max. That is 2 over the norm of the Hessian. So learning rate has to be sufficiently small. Okay. And then if you choose the optimal learning rate, then the convergence is kappa minus 1 over kappa plus 1. That's the one you also had that in yesterday's talk. So kappa is the condition number of the Hessian. Okay. So the speed of convergence depends on the condition number of Hessian. In deep learning, the learning rate is usually chosen by tuning. So you can, with tuning, you try out different, you usually can get pretty close to the optimal learning rate. So usually you could get to that kappa minus over kappa plus 1. But even you get to that, it's going to be very slow with ill-conditioned Hessian if kappa is very large. So so here's things we do in numerical analysis. Of course, do preconditioning to improve. If you have ill-conditioned matrix, you change the conditioning by preconditioning. So in this context, you consider a change of variables, so theta is pz. Then I rewrite the loss as a function of zl pz. And then I can do gradient descent in z. Then it's z like this. Then if you write out the gradient in z, it's just p transpose times the gradient in theta. Multiply p from the left through the equation, then pzk is theta k. So going back to the original parameter theta. So we get to this recurrence that's in the original coordinate theta rather in z. So it's an implicit transformation. Okay, we don't actually carry out the transformation explicitly. The net effect is that you multiply the gradient by this pp transpose. So if I have a transformation with p, now with this transformation, the benefit of that is that the rate of convergence now changed to this is the kappa prime. The condition number kappa prime now is the condition number of the Hessian with respect to the variable z, and the Hessian of the loss with respect to variable z can be written as p transpose times the Hessian, original Hessian with respect to theta times p. Okay, so with that transformation, I effectively transform the Hessian to p transpose times p with that. So that allows us to do preconditioning. That is to choose p such that that transformation transformed Hessian will have better condition number, right? So that's what we're going to set out to do. Oh, before I do that, well, we wrote the paper, we sent it for review, and then the referee points out, well, this theory doesn't apply to neural network because in the neural network, the ReLU-based neural network has the property that Hessian is theoretically singular. It's always singular. The lambda mean is always 0. It has something called scaling invariant properties. So we have to look at that, and then it turns out we can modify the theory to make it still work with respect to the neural network. So I'm going to quickly show you that how we can do that. Okay. So let me first look at how the Hessian becomes singular. So if you look at two layers of neural network, so here say layer L-1 and layer L, well, then HL is defined from HL-1 like that, and HL+1 defined like that. And then if it's a ReLU network, G is ReLU, then I take any positive diagonal matrix D, multiply on the first equation there, DHL. Then if it's a positive diagonal matrix, you can pull that inside G, because G for positive number, G is linear. The ReLU function, if it's a positive scalar, you can pull that in, it's just linear. So you can pull that D inside. So you got this. And then for the next layer, the HL-1, I can insert the D inverse and D in between there. So if you look at this network now with HL-1 to HL+1, and now if I change the two parameters, so the WL and BL is multiplied by D, and simultaneously I multiply WL+1 BL, actually just WL+1 from the right by D inverse, then this network will produce the same outcome as the other network. So the output is invariant under this scaling, the diagonal scaling. Okay. So I mean, in general, neural network is over parameterized. So there are a lot of things like that. So if you have something like that, then here's how we look at it. So if I look at one parameter theta 0, so I look at all of its invariant scaling, so all the scaling like that, then it calls a function of t. So it's actually a manifold. You collect, if for each parameter you have all the invariant scalings, okay? It's a function sum t. So if you look at the parameter space, for every point, there's a manifold going through that point. They all produce the, I mean, every parameter on the manifold produce the same output, okay, have the same input output. So in that case, the loss is constant for all the parameters on that manifold, right? Because they all produce the same output. So, so if theta star is a local minimizer, then every point on that manifold is a local minimizer. Then the gradient at every point on that manifold would be 0. Take the derivatives, you got Hessian times dt theta star t is going to be 0. So that dt star t is in the null space of the Hessian. So Hessian has a null space. The null space contains the column space of the basically the tangent space of that manifold. So because of that, the theory that we talk about, the condition number based, the theory doesn't apply because you know the lambda mean is going to be 0. It turns out we can modify the theory to state like something like this. So because of this special case, so if I assume that's the scaling invariant is the only reason for the singular Hessians, that is the null space of the Hessian is exactly the column space of that, then the conversion bound still holds with the same R, but lambda mean now can be replaced by lambda mean star, and lambda mean star is the smallest non-zero eigenvalues of the Hessian. So basically you can wipe out those 0 eigenvalues. So project out those 0 eigenvalues. I quickly show you the idea and then we'll move on. So for each theta k, if you look at the gradient descent, so at each step, say theta k, I look at theta k. Remember theta k, there's at every point there's a manifold going through it. So the entire manifold has the same loss. So instead of I look at the local minimizer. So instead of looking at the error between theta k and the fixed local minimizer, say the star, I'm going to look at the manifold going through that theta star, and then look for the one that's closest. So I look at it, call it theta k star. So theta k star is the one on that local minimizer manifold that's closest to theta k. Okay. Then theta k minus theta k star. This is the error vector would be perpendicular to the tangent space. And if you have that, then if you go through the proof of the error bound that we have, basically you write that as this I minus alpha times the Hessian times theta k minus theta k star. But now theta k minus theta k star is perpendicular to the tangent space, but tangent space is the null space of the Hessian. So we can project that out. So if you project that out, then because this is orthogonal to the null space of the Hessian, then you can replace the bound. Instead of using the lambda mean, you can use the lambda mean other than those 0 eigenvalues. Okay. So basically that's the idea. So the condition number based theory still works for the ReLU network. Okay. Now let's go back to the how to use this to do the preconditioning. Okay. So in order to do preconditioning, we need to know a little bit about Hessian. So it turns out if you look at the Hessian of all the parameters, it's going to be super complicated, so you're not going to get much out of it. But if we look at the Hessian with respect to one's weight and bias, then there's some certain structure we can find out and then can be explored for preconditioning. So let's look at one layer. And then I'm going to look at one row of the weight matrix WL. So call that WI. The notation is going to be very complicated, but just bear with me. So WIL transpose is one row, ice row of WL, and then BIL will be the ice entry. Then I look at the corresponding output of that layer, the ice entry, AIL, just the linear part. I can write it as W hat times H hat. W hat just put the bias and the weight together, and H hat is just the H L minus the H, the hidden that going to the layer, add 1 on the top. If we do that, then we look at the Hessian, then just some algebraic calculations we'll see, because the loss is the mean loss over the mini batch. So because of that loss structure, then the Hessian has this structure. The Hessian is this H hat matrix on the right and H hat transpose on the left with S in the middle, a diagonal matrix S in the middle. The H hat is just those the hidden variables, the n of them, take transpose as a row of them, n row of this, put them together, and add 1 to the first column. And the diagonal matrix X is the second order derivative of the loss. So the Hessian of the loss has this structure. Now this H hat matrix, it has something that has a structure that you probably have seen a lot, because very often, even like linear regressions or logistic regressions, we have a matrix like that coming up. So for example, for linear regression, actually, so that's just input, and then S is just identity. So we usually call A transpose A. So just something like that. So it kind of just generalize that to a neural network. Okay. Okay. So actually, one more thing. So we want to improve the conditioning of Hessian matrix. This one here, by left multiply P transpose and right multiply P to improve that condition number. The middle matrix S here, there's not much we can do. It contains second order derivative, also depends on those things. It's complicated. But this H hat is the one we can try to improve the condition number. Okay. So what we're going to do now is to try to improve the condition number of the matrix H hat. How do we improve that? Well, we use this transformation P. So take a transform W hat as PZ. So using, that's the same notation. Okay, state as PZ earlier, so it's not W hat is PZ. The preconditional matrix P is U times D. So U, what is U? What is D? U is just a diagonal 1, and then which is a block upper triangular, and then with mu A being the mean of the mini batch of the hidden HL minus 1, and then minus mu A transpose on the top right corner, U there. So basically put a mean here, and then the variance, so standard deviation here, construct it as a diagonal matrix, and then D is the inverse of that. So basically just divided by standard deviations. All right, so if I use this, construct this P, what happened to the Hessian? Here's what we have. So if I multiply P transpose P on the Hessian, the H hat after multiplied by P changed to G hat, call it by G hat. So what is G hat? G hat just has the same structure as 1, 1, 1, and then G1 to Gn. And this is obtained by multiplying those matrices together. So if you just do some algebra, you'll find if Gj is just the normalization of Hj. So you just subtract every each hj by its mean, and then divide by the standard deviations. Okay. So basically, the effect of this transformation is I transform the Hessian, which was defined by a general h hat, to something that's defined by g hat. So it's implicitly I change the hidden variables, just like a batch normalization, but I do that implicitly. And a g hat is now normalized activation. So it's kind of implicitly change the activation for the purpose of Hessian. Okay. Okay, so why is this transformation good? So we're going back to numerical linear algebra now. So we're going to show this actually improves the conditioning of that H hat matrix. So first, the one that's multiplied by U, the U matrix there, what it does to the H hat matrix is really just subtract H by the mean. So each HI is subtracted by the mean. Again, Joseph had this morning slides has slides on that X1. So if subtract each activation by mean, then it's equivalently to say E transpose times that H minus E mu A transpose. The result of that is 0. There is, or another way to say it, it's centered at 0 after subtract out the mean. So the mean becomes 0. The mean is 0. That means the in terms of matrix here, the first column is orthogonal to the remaining columns. That's what it is when you center that. So the first column is orthogonal to the. So it's basically an orthogonalization process. Okay. So when you do that centering, it just do the orthogonalization against the first column. So we know if we make it more orthogonal, the condition number should be better. So we can actually prove that. And then after that, sigma A is the standard deviations. The standard deviation turns out it's a vector here, okay? Because each hj is a vector. Then if each entry there is just the norm of the columns of the H minus E mu A transpose, that matrix there, the normalized. So it turns out in terms of this matrix, just columns divided by square root of n. Okay. So actually, let me. So when I normalize that centered activation by the standard deviations in terms of matrices, I just normalize each column to have norm square root n. Okay. So that all columns, the first column of course also has norm square root n. So in that way, all columns have the same norm. Okay. And that's another way that condition number can be improved. So here's the theorem. So the first statement says basically orthogonalization improve the conditioning. It should be very straightforward actually, but it takes quite a bit of proof. We haven't seen a result like this before in the literature. I don't know, Joseph, if you know any available result. But intuitively, it seems quite straightforward. When you do the orthogonalization, it should improve the conditioning. But using minimax can be proved. And then the other ill conditioning is caused by typically another reason for ill conditioning of matrix is because of the ill scaling, different scaling of a matrix. So if it's columns, some columns have have very different scaling from others, then the matrix tends to be ill conditioned. In terms of the statistics is to say if the standard deviations for different components of that hidden variables have very different scale, then the Hessian, the H hat matrix would be very ill conditioned. So what we do is just by normalizing that, making it all have the same norm, that should improve the conditioning. Okay. In fact, there's a classical result by van der Sloot. You cannot say normalize all the columns to have the same norm. You cannot say condition number is definitely improved, but it's within a small factor of the optimal condition number. So that's a theorem of van der Sloot's. So with the optimal scaling condition number times the square root k plus 1, you know it's definitely better than that. So that's a transformation that actually improved the conditioning. Okay. So here's a algorithm to implement this. So basically, when we do preconditioning, everything stays the same. The only thing different is we apply that preconditioning transformation on the gradient. That's all. You transform the gradient. You don't need to do anything else. So all we need to do is here's how we transform the gradient. So at the layer L, at the training step, so if I have, this is the input to the layer, and I get the gradient with respect to weight and bias, and then I computed statistics for the for that layer activations, and actually to make things more smooth, we use some sort of running average of the mean and variance, and then add something small to prevent division by 0, and then apply the P transpose P. P transpose P is all those it's very simple matrix, diagonal and a rank 1 matrix. So it's actually it comes down to this simple update in the last line, the step 4 there. Okay, so that's the what we call BMP algorithms. So this framework can be applied to other kind of architectures. So for example, convolutional neural network. So if you apply this derivation, it turns out that the mean and variance need to be slightly different. Because the H hat matrix, if you have a convolutional network, then the H hat matrix would be the activation there are different. So, but it will naturally lead to using mean and variance of the hidden for CNN. The hidden variable is a tensor, so 3D tensors. So in that case, our derivation would naturally lead to use the mean and variance of the tensor in the mini-batch direction and the spatial dimensions. So and this is how actually BN is used in CNN, but really not quite the same as the BNN. I mean, how the BN is derived for the dense network or fully connected network, the basic network that we talk about. All right, so let me show you some experiments. So I'm going to show you one data set of CIFAR-10. We did the experiment for several data sets. Let's just look at the simple ones. So here's a 5 layers CNNs, so 3 convolutional layer and then 2 dense layer. So we compared just here compare three things. One is vanilla network, plain network, nothing else, and then BN, batch normalization network, and then BMP, our preconditioning methods. The dash line, there's training loss, how training loss against the epochs. So you see all 3 converges. The blue line there is vanilla network, and the red line is BN, improved that quite significantly. And the BMP actually is doing a little bit better in training than BN, the black line there. The shaded area is the range, the maximum minimum over 5 random runs. But in machine learning, more interesting thing is actually testing. So the solid line there is the testing accuracy for this. Oh, by the way, CIFAR-10 is the 10 class classification of images. So you see there the blue line there significantly slower than the red line and the black line. But at the end, they're all about the same in this case for the small network. Okay. Yeah.
When you're setting those, firing that manifold for that,
Mm-hmm.
are you tempering it at all, or it looks like maybe struggling to learn that manifold?
What do you mean?
Like, are you any sort of tempering, or are you just applying that manifold fairly epic going forward?
Let me. Our method preconditioning. I mean, the advantage of our method is we do not change anything about the network parameter, nothing. Everything is like as it is. So if it doesn't want to mean tampering with the, we don't do it. We don't change anything. We only change the gradient. We change the direction of the gradient. Instead of taking the gradient as is, we apply that transformation, so that to make it change faster, to change to converge faster.
But you're kind of learning that precondition, right?
Yeah. But we use that statistics of the activation. But BN, so to your point, the BN actually changed the network. So the network, the inserting something, artificially inserting something into the network. So that's why it's harder to understand theoretically. Yeah, does that answer your question? Okay. Yeah, okay, let's talk about it. Now, the one that I just showed you is the one with mini batch size 128, which is a typical one. Okay. But we also test one on a very small mini batch size. So it's mini batch size 2. Nowadays, I mean, with model become larger and larger, sometimes it's desirable to use small mini batch in order to fit memory into a GPU or something like that. You may want to use a small mini batch. So, but in this case, you can see here's the same network, but just with smaller mini batch size. So you see that the blue lines is the vanilla network, black lines are preconditioning, but BN in this case doing terribly. As I mentioned, because the network is very dependent on the mini batch. So that was a basic network. So here's a one where the batch normalization has been most successful. Used is in the ResNet. Batch normalization basically pushed ResNet to get the state of result. So we also tested on the ResNet. So here's a 110 layer ResNet. Dash lines, the training there, more or less the same for all three methods. And BN initially doing slightly better than the green line there is actually we compare with the group norm, which is another normalization methods. So the vanilla network was doing very, very bad. So I took it up. But this is incorporating something called learning rate decay. So at epoch 80 there's a learning rate decay by 1/10. So there's a big drop in the accuracy and the big increase in the big drop in the loss and the big increase in the accuracy. And there's another learning rate decay at the 1/20th epoch. So at the learning rate decay, BN is doing much better than everybody else. Has a big jump, yeah.
This one, we had for some curves, accuracy that starts high and then goes down.
You mean? Oh, here it goes down overfitting. Yeah, overfitting. Yeah, it's overfitting. Overfitting.
Overfitting. Oh, I see. The lower stuff is 95%.
No, the left is the accuracy, the right axis is the loss. Yeah. Test accuracy, the solid lines test accuracy, yeah. So I only show you 20 epochs. If I show you more, it actually goes down more. Yeah, training loss will continue to go down. The dashed line there is training loss. So if I continue training, the training loss will go down, but leveling off. But then actually right around there, if I do more training, the testing accuracy wouldn't increase. It actually would gradually decreases. It's overfitting. Yeah. So so I mean, rest now you have to this learning rate decay that should help. I think I have a few minutes. So quickly, I want to show you a condition number analysis. So here is a very simple, fully connected network, just 2 layers, and then so that we can look at the Hessian matrix. So here's the still for C410 data set. So again, we look at vanilla versus BMP in this case. So the blue line is the vanilla network, and then black line is the BMP. So again, training accelerated. But if you look at the condition number, so here's the plot of condition number. The blue line is the condition number vanilla network, and then the black line is the precondition. So you see there's it's still very large, 10 to the 11, but it roughly improved the condition number by 10 orders of magnitudes. So it's basically when you have activations that varies by 10 to the 10, that's what you will expect. All right, so let me just quickly complete with some conclusions. So we have a theoretical preconditioning framework that can be used in the neural network training. So in most cases, it's comparable to batch normalization, but for small mini batch, we outperform batch normalizations. And it has some relations to batch normalization, so it also provides some theoretical justification for batch norm. But one advantage of our method is it's a general framework, so you can use in any kind of architectures, CNN, group, graph neural network, and things like that. So finally, here's a reference for our paper. Thank you. Yeah. Mm-hmm. Mm-hmm.
One of them is you quite get the whole picture about how we get the conditioner. Is this some sort of low rank?
Yeah, it's the one's low rank. Well, no, I mean, it's low rank modification, rank 1 modification. So it's just a diagonal. Yeah, just diagonal, and then it's just diagonal basic identity, and then with 1 row vector. So it's a rank one perturbation to the identity. Yeah, just 1. Yeah. So what that does is it just subtract the mean from all the activations. Yeah.
So yeah. My next question is you do this for each mini batch, right?
Mm-hmm. Yeah.
So how do you restore these?
We store that, yeah. We store that, yeah. I mean, we don't have. I mean, I can just compute with every mini batch. If you just compute the mu a and mean and variance for that iterations, then I don't need to store that. I can do that without storing. But the way we implement it, actually, we take a running average of the mean and variance. Because for small mini batch, so the experiment I showed there with mini batch 2, then it's very volatile. The mean and variance is very volatile. They change a lot. So we don't want preconditioning to be too volatile. So we just use the running mean and variance. So that's one advantage of our method over the batch norm, because batch norm you cannot. It has to be because it's built into the network, so it has to be that mean and variance of that. Yeah. Yeah. That's it. Mhm.
So because otherwise, if you just keep the current, the ordering of your data will matter, right? At the beginning, they may have very large mean or something. That will affect how the preconditioner will be acting,
Yeah.
right?
Yeah. That's true. I mean, generally, if I have small mini batch size, it varies a lot. So now, because neural network training usually takes long iterations. I mean, I showed like 20 epochs, but each epoch is something like 1,000 iterations or something like that. So it's actually lots of iterations. So initially, these things, it takes a while to settle down. Yeah. So that's true. Yeah.
It was almost your last slide when you were showing the condition. Before you projected out the zero values.
Oh, so good question. So we actually look at this just single weight. This just look at one weight and bias. So actually, in that case, you don't expect that to be singular. Oh, how do you get that? Okay. I can't say definite, but because of this yield conditioning, because of the best scaling, and I was thinking the QR algorithm can compute if a matrix, I believe if it's called, I think Stewart has a paper. If it's a badly graded, then the QR algorithm can compute small eigenvalues quite accurately. I assume that's what happens. I mean, so yeah. I mean, when you look at 10 to the 26, you have to wonder. So I kind of wonder. Well, but that's what machine return us. But we did have another plot. I didn't show you here. It's just the diagonal matrix, the variance matrix. So that variance matrix has for those cases has like whatever about 10 to the 10 to 11 order of magnitudes. So I think it's because of the QR algorithms. If I assume it's the PyTorch that they use QR, that for the graded matrix that they are able to compute small eigenvalues accurately. Yeah. Yeah. Yeah, because I normalized the mean and variance. They varies a lot with the mini batch. So so we can, by normalizing it, we kind of take that out, take that part of the variance away. So it's more or less constant. Yeah. I think that's what happened. Yeah. Yeah.
I was wondering how to compare this with other optimizers like
some of them already incorporate. No, it already incorporate like our method for ours. For example, ResNet experiment, we had the momentums, and the ResNet also used momentums. And the other one, I think we use RMS prop. So it's tuned. All the methods are tuned with respect to the optimizer and the learning. Yeah.
This one, RMS prop and edit was actually very similar.
Yeah. Somehow it doesn't work well. The BMP doesn't work well with Adam. So so that's one thing. We don't know why, but yeah.
Okay, let's think. So Qiang